And welcome back. And this time we're looking at Euclid's solution to the equation ax plus x squared is equal to b squared. Or in Euclid's language, can we find an unknown number such that a rectangle made with this unknown number and a known number a plus the square of this unknown number, will that be equal to a fixed known square value? So what we're saying here is, give me a known value. Can we find something that we can add to this with the value of x such that when I complete this rectangle and add the square that this makes, that this rectangle is in fact equal to a predetermined value for b squared? That's what Euclid's up to. And in our language, this turns into the equation a times x plus x squared is equal to b squared. Now, using the discriminant on this, we realize that there are no restrictions on a and b. So a can be any length, b can be any length, and there's no problem with this. So let's take a look at exactly what Euclid is going to do to try to find this missing value. And with the magic of video, I was able to erase the board and we can begin looking at our solution. And we're going to begin by looking at what is the length of a. And so I've already made a and b up here, but these are my controls. This is nothing more than a copy of this value of a. And we're going to look at how we go through making this solution that Euclid came up with. So on A, we're going to affix a length B. At the end of A, we're going to stand up a perpendicular of length B. So before I go any further, let's take a look at these two lengths. So I can play with A. I can also play with B. And as I said, there's no restrictions on the ratio between A and B. Now then, in order to come up with a solution, Euclid said, well, there's not a lot I can do here. Let me find the midpoint of one of the segments, namely A. So that's what we're going to do next. We're going to find the midpoint on A. Now, from the midpoint on A, I'm going to center a circle, and that circle is going to pass through this topmost part of the segment representing B. And this is going to help us see the solution. And what I've done is I've extended the segment A using one of Euclid's axioms. You can extend any finite straight line. And so this little bit right here, Euclid would say, that's the missing piece. This is going to help me make my rectangles. In other words, here's the unknown value x. Now let's see exactly how that's going to look. So let's build the rectangle A by x. And all I've done is, and I hid this, was I took this distance and I went down the same amount of distance and created this rectangle. And this rectangle has an area of a times x. Now then we're going to complete the square of the unknown. And so all of this is great. So here's my ax plus x squared. Now the question is this equal to b squared? Well, I don't see b squared, so let me put it up here. And there is my value for b squared. So the claim that we're making is that I have squared this rectangle because I've taken this rectangle and basically I actually started with the square, and I've gone backwards from squaring a rectangle to going and saying, hey, from a square, I can build the rectangle that has the equal area. Let's take a look. You may not believe me. So what I'm going to do is I'm going to take these two areas down here, and I'm actually going to measure them. And we'll look at this area. And I'm going to grab these and pull them down so we can look at these numbers. Now, this being the case, this is going to help me see that when I grab this, and I come up here and I decide to do a measurement of an area, and you say, hey, I don't see equal numbers. But wait a minute, we said the rectangle plus the square. So I'm going to have to come up here and do a calculation. And my calculation is going to be the area of the rectangle plus the area of the square. And I now see I have 4624, which is the same I have here. And if you think I came up with just the one time it works, I can adjust the length on B to give us different solutions for different values of A and B. Now, what makes this so impressive in my mind is the fact that the Greeks were basically taking geometry and they're doing what we consider college algebra, which is not all that simple. Go ask some of the students that take college algebra from time to time. So we actually see how the Greeks are using algebra as basically a extension of their geometry. And this is how math is going to be done for a very long time, where math will be married to geometry or to some form of physical relationship. We're not looking at math as a totally theoretical, abstract topic. This will not come around until the 1700s, at about the time of Sir Isaac Newton. More on him later. I hope this helps.